So what about artificial intelligence? Would it be the EMs, the emulated minds? What idea, whether that struck you in the shower one day, or
Well,
that you just
clearly the
observed?
biggest viewquake in artificial intelligence is the realization of just how complicated our human minds are. So most people who come to artificial intelligence from other fields or from relative ignorance, a very common phenomenon, which you must be familiar with, is that they come up with some concept and then they think that must be it. Once we implement this new concept, we will have it. We will have full human level or higher artificial intelligence, right? And they're just not appreciating just how big the problem is, how long the road is, just how much is involved. Because that's actually hard to appreciate. When we just think, it seems really simple. And studying artificial intelligence, going through many particular problems, looking at each problem, all the different things you need to be able to do to solve a problem like that, makes you realize all the things your minds are doing that you are not aware of. That's that vast subconscious that you're not aware. That's the biggest view cave from artificial intelligence by far for most people who study artificial intelligence, is to see just how hard it is.
I think that's a good point, but I think it's a very early viewquake. It's when the
Sure.
Dunning-Kruger crashes hard. It's the first realization that humans are actually quite incredible. The human mind, the human body is quite incredible.
There's a lot of different parts to it.
But then, see, it's already been so long for me that I've experienced that viewquake that for me, I now experience the viewquakes of, holy shit, this little thing is actually quite powerful. Like neural networks. I'm
Yeah.
amazed because you've become
Sure.
almost cynical after that first viewquake of like, this is so hard. Like evolution did some incredible
Right.
work to create the
Yes.
human mind. But then you realize, just like as you've talked about a bunch of simple models, that simple things can actually be extremely powerful. That maybe emulating the human mind is extremely difficult, but you can go a long way with a large neural network. You can go a long way with a dumb solution. It's that Stuart Russell thing with the reinforcement learning.
Right.
Holy crap! You can go
You
quite a long way with a
right.
simple
But we
thing.
still have a very long road to go. But
Wow.
nevertheless,
I refuse to sort of know the road. The road is full of surprises. So long
sure.
is an interesting, like you said, with the 6 hard steps that humans had to take to arrive at where we are from the origin of life on Earth. So it's long maybe in the statistical improbability of the steps that have to be taken, but in terms of how quickly those steps could be taken, I don't know if my intuition says if it's hundreds of years away or if it's a couple of years away. I prefer to measure.
Pretty confident it's at least a decade. And
we could
mildly confident it's at least 3 decades.
I can steel man either direction. I prefer to measure that journey in Elon Musk's. That's the new.
Well, we don't get Elon Musk very often, so that's a long time scale.
For now, I don't know. Maybe you can clone, or maybe multiply, or I don't even know what Elon Musk, what that is. What is that? What is?
That's a good question. Exactly. Well, that's an excellent question.
How does that how does that fit into the model of the 3 parameters that are required for becoming a grabby alien civilization?
That's the question of how much any individual makes in the long path of civilization over time.
Yes.
And, it's a favorite topic of historians and people to try to focus on individuals and how much of a difference they make. And certainly some individuals make a substantial difference in the modest term, right? Certainly without Hitler being Hitler in the role he took, European history would have taken a different path for a while there. But if we're looking over many centuries longer term things, most individuals do fade in their individual influence.
So,
even Einstein.
Even Einstein, no matter how sexy your hair is, you will also be forgotten in the long arc of history. So you said at least 10 years. So let's talk a little bit about this AI point. Of how hard is the problem of solving intelligence by engineering artificial intelligence that achieves human-like qualities that we associate with intelligence. How hard is this? What are the different trajectories that take us there?
one way to think about it is in terms of the scope of the technology space you're talking about. So let's take the biggest possible scope, all of human technology, right? The entire human economy. So the entire economy is composed of many industries, each of which have many products with many different technologies supporting each one. At that scale, I think we can accept that most innovations are a small fraction of the total. That is, usually you have relatively gradual overall progress, and that individual innovations that have a substantial effect on the total are rare, and their total effect is still a small percentage of the total economy, right? There's very few individual innovations that made a substantial difference to the whole economy, right? What are we talking? Steam engine, shipping containers, a few things.
Shipping
containers deserves to be up there with
one.
steam engines, honestly.
Can you say exactly why shipping containers?
Shipping containers revolutionized shipping. Shipping is very important.
But placing that at shipping containers. So you're saying you wouldn't have some of the magic of the supply chain, all that, without shipping containers?
It made a big difference. Absolutely.
Interesting. That's something to look into. We shouldn't take that tangent, although I'm tempted to. But anyway, so there's just a few innovations.
Right. So at the scale of the whole economy, right? Now, as you move down to a much smaller scale, you will see individual innovations having a bigger effect, right? So if you look at, I don't know, lawnmowers or something, I don't know about the innovations lawnmower, but there were probably like steps where you just had a new kind of lawnmower, and that made a big difference to mowing lawns because you're focusing on a smaller part of the whole technology space, right? So, and sometimes like military technology, there's a lot of military technologies, a lot of small ones, but every once in a while, a particular military weapon like makes a big difference.
Mm-hmm.
But still, even so, mostly overall, they're making modest differences to something that's increasing relatively steady. Like U.S. military is the strongest in the world consistently for a while. No one weapon in the last 70 years has like made a big difference in terms of the overall prominence of the U.S. military, right? Because that's just saying, even though every once in a while, even the recent Soviet hyper missiles or whatever they aren't changing the overall balance dramatically, right? So when we get to AI, now I can frame the question, how big is AI? Basically, one way of thinking about AI is it's just all mental tasks. And then you ask, what fraction of tasks are mental tasks? And then I go, a lot. And then if I think of AI as like half of everything, then I think, well, it's got to be composed of lots of parts where any one innovation is only a small impact, right? Now, if you think, no, AI is like AGI. And then you think AGI is a small thing, right? There's only a small number of key innovations that will enable it. Now you're thinking there could be a bigger chunk that you might find that would have a bigger impact. So the way I would ask you to frame these things in terms of the chunkiness of different areas of technology, in part in terms of how big they are. Like if you take 10 chunky areas and you add them together, the total is less chunky.
Yeah. But are you able, until you solve the fundamental core parts of the problem, to estimate the chunkiness of that problem?
Well, if you have a history of prior chunkiness, that could be your best estimate for future chunkiness. So, for example, I mean, even at the level of the world economy, right? We've had this, 10,000 years of civilization. Well, that's only a short time. You might say, oh, that doesn't predict future chunkiness. But, it looks relatively steady and consistent. We can say even in computer science, we've had, 70 years of computer science. We have enough data to look at chunkiness in computer science. Like, when were there algorithms or approaches that made a big chunky difference? And, versus, and how large a fraction of that was that? And I'd say mostly in computer science, most innovation has been relatively small chunks. The bigger chunks have been rare.
Well, this is the interesting thing. This is about AI and just algorithms in general is, page rank. So Google's,
right?
So sometimes it's a simple algorithm that by itself is not that useful, but the scale
context
in a context that's scalable, like
right.
depending on the context, is all of a sudden the power is revealed. And there's something, I guess that's the nature of chunkiness, is that you could things that can reach a lot of people simply can be quite
So
chunky.
one standard story about algorithms is to say algorithms have a fixed cost plus a marginal cost. And so in history, when you had computers that were very small, you tried all the algorithms that had low fixed costs and you look for the best of those. But over time, as computers got bigger, you could afford to do larger fixed costs and try those. And some of those had more effective algorithms in terms of their marginal cost. And that, in fact, that it roughly explains the long-term history where, in fact, the rate of algorithmic improvement is about the same as the rate of hardware improvement, which is a remarkable coincidence. But it would be explained by saying, well, there's all these better algorithms you can't try until you have a big enough computer to pay the fixed cost of doing some trials to find out if that algorithm actually saves you on the marginal costs. And so that's an explanation for this relatively continuous history so we have a good story about why hardware is so continuous, right? And you might think, why would software be so continuous with the hardware? But if there's a distribution of algorithms in terms of their fixed costs, and it's, say, spread out in a wide log normal distribution, then we could be sort of marching through that log normal distribution, trying out algorithms with larger fixed costs and finding the ones that have lower marginal costs.
So would you say AGI, human level AI, even emulated minds, is chunky? Like a few breakthroughs can take us
an
quite
M
far.
is by its nature chunky in the sense that if you have an emulated brain and you're 25% effective at emulating it, that's crap. That's nothing. Okay. You pretty much need to emulate a full human brain.
Is that obvious? Is that obvious?
I think it's pretty obvious. I'm talking about so the key thing is you're emulating various brain cells. And so you have to emulate the input-output pattern of those cells. Yeah. So if you get that pattern somewhat close, but not close enough, then the whole system just doesn't have the overall behavior you're looking for, right?
But it could have functionally some of the power of the overall system.
So there'll be some threshold. The question is, when you get close enough, then it goes over the threshold. It's like taking a computer chip and deleting every 1% of the gates, right?
No, that's very chunky. But the hope is that emulating the human brain, the human brain itself is not...
Right. So it has a certain level of redundancy and a certain level of robustness. And so there's some threshold when you get close to that level of redundancy and robustness, then it starts to work. But until you get to that level, it's just going to be crap, right?
Yeah.
It's going to be just a big thing that isn't working well. So we can be pretty sure that emulations is a big chunk in an economic sense, right? At some point, you'll be able to make one that's actually effective in enable substituting for humans. And then that will be this huge economic product that people will try to buy like crazy. Now,
it'll bring a lot of value to people's lives, so they'll be willing to pay for it.
Well, but it could be that the first emulation costs $1 billion each, right? And then we have them, but we can't really use them; they're too expensive. And then the cost slowly comes down, and now we have less of a chunky adoption, right? That as the cost comes down, then we use more and more of them in more contexts, and that's a more continuous curve. So it's only if the first emulations are relatively cheap that you get a more sudden disruption to society. And that could happen if sort of the algorithm is the last thing you figure out how to do or something.
What about robots that capture some magic in terms of social connection? The robots, like we have a robot dog on the carpet right there. Robots that are able to capture some magic of human connection as they interact with humans, but are not emulating the brain. What about those? How far away?
So we're thinking about chunkiness or distance now. So if you ask how chunky is the task of making a emulatable robot or something,
which chunkiness and time are correlated,
right? But it's about how far away it is or how suddenly it would happen. Chunkiness is how suddenly, and difficulty is just how far away it is. But it could be a continuous difficulty. It could just be far away, but we'll slowly, steadily get there. Or there could be these thresholds where we reach a threshold and suddenly we can do a lot better.
Yeah, that's a good, question for both. I tend to believe that all of it, not just the M, but AGI too, is chunky. And human level intelligence,
so my best
embodied
guess
in robots, is also chunky.
Is the history of computer science and chunkiness so far seems to be my rough best guess for the chunkiness of AGI.
Yeah,
that is,
it is chunky.
It's modestly chunky, not that chunky, right? Our
Like
ability to
chunky
use
peanut
computers
butter,
to do
I'm
many
hungry.
things in the economy has been moving relatively steadily. Overall, in terms of our use of computers in society, they have been relatively steadily improving for 70 years.
No, but I would say that's hard. Well, yeah, okay. Okay, I would have to really think about that because neural networks are quite surprising.
Sure, but every once in a while we have a new thing that's surprising. But if you stand back, we see something like that every 10 years or so, some new
The progress
innovation
is gradual.
that has a big effect.
So moderately chunky. Huh. Yeah.
The history of the level of disruption we've seen in the past would be a rough estimate of the level of disruption in the future, unless the future is we're going to hit a chunky territory, much chunkier than we've seen in the past.
Well, I do think there's it's like Kuhnian, like revolution type. It seems like the data, especially on AI, is difficult to reason with because it's so recent. It's such a recent field.
Well,
In this
AI has been around for 50 years.
I mean 50, 60, 70, 80 years being recent.
Okay.
That's how I'm.
It's enough time to see a lot of trends.
A few trends. I think the internet, computing, there's really a lot of interesting stuff that's happened over the past 30 years that I think the possibility of revolutions is likelier than it was in the...
I think for the last 70 years, there have always been a lot of things that look like they had a potential for revolution.
So we can't reason well about this.
I mean, I think we can reason well by looking at the past trends. I would say the past trend is roughly your best guess for the future.
But if I look back at the things that might have looked like revolutions in the 70s and 80s and 90s, they are less like the revolutions that appear to be happening now, or the capacity of revolution that appear to be there now. First of all, there's a lot of more money to be made. So there's a lot more incentive for markets to do a lot of kind of innovation, it seems like, in the AI space. But then again, there's a history of winters and summers and so on. So maybe we're just like riding a nice wave right now.
One of the biggest issues is the difference between impressive demos and commercial value.
Yes.
So we often, through the history of AI, we saw very impressive demos that never really translated much into commercial value.
Listen, as somebody who works on and cares about autonomous and semi-autonomous vehicles, tell me about it. And there again, we return to the number of Elon Musks per Earth per year generated. That's the M. Coincidentally, same initials as the M. Very suspicious. Very suspicious. We're gonna have to look into that.